What's going on, everybody? Got another math video here for you. This is maximum and minimum values, multivariable calculus. All right, so let's go ahead and get started. So let's look at this definition here. It says a function of two variables has a local maximum at AB if f of xy is less than or equal to f of AB when xy is near AB. The number f of AB is called a local maximum value. If f of xy is greater than or equal to f of AB when xy is near AB, then f has a local minimum at AB, and f of AB is a local minimum value, which that makes sense. If f of AB is the largest value near this point, then it's a local maximum. And if it's the smallest, if f of AB is less than all of them near AB, then it's a local minimum. All right, well, let's look at this theorem here. It says if f has a local maximum or minimum at AB and the first order partial derivatives of f exist there, then the partial with respect to x and the partial with respect to y evaluated at AB is equal to 0. Okay, so that's gonna come in handy there. And we have a note here. A point AB is called a critical point or stationary point of f if the partial with respect to x of AB is equal to 0 and the partial with respect to y of AB is equal to 0, or if these partial derivatives does not exist. The previous theorem says that if f has a local maximum or minimum at AB, then AB is a critical point. It's a critical point of f. However, as in single variable calculus, not all critical points give rise to maxima or minima. And you saw that in single variable calculus where you would have critical numbers, but sometimes it may not. But remember, at that critical number, when you did those tests, it might be increasing to the left and to the right of that critical number, and so there was no maximum or minimum there. So it's the same thing here. All right. So let's get started with some examples. All right, so it says find the extreme values of f of xy equal x squared plus y squared minus 2x minus 6y plus 14. All right, so what does it say to do? We need the partial with respect to x and the partial with respect to y, and then we'll take that and we'll set those equal to 0. That's going to give us our critical point. All right, so I've got the partial with respect to x is equal to 2x minus 2, and the partial with respect to y is equal to 2y minus 6. And if we set these equal to 0, I get x equal 1, and 2y minus 6 equals 0, I get y equals 3. So I have a critical point at 1, 3. Okay. Now, is this a maximum or minimum value? A local max or local min? Can we tell? Well, let's look and see what we have here. Okay, let's take our function here and let's rewrite it. So I've got f of xy is equal to x squared minus 2x plus y squared minus 6y plus 14. And you can always tell what we're going to do when we put the parentheses around, when we group the x's and y's together and put those parentheses and leave a little space there. We're going to complete the square on it. So if I take the 2, I half it, that's 1. 1 squared is 1, so I add 1. So that means I got to come over here and subtract 1. And then I half the 6, that's 3. 3 squared is 9, so I add 9. So that means I have to come over here and subtract 9. So I get f of xy is equal to x minus 1 squared. I'll tell you what, let's write it like this. This right here is going to be 4, right, when I combine the numbers, plus x minus 1 squared plus y minus 3 squared. Okay? All right, so let's make some observations here, okay? So we know that f of xy is greater than or equal to 4 for all values of x and y. Okay, we know that. And how do we know that? Well, because we know that this term here and this term here is either going to be 0 or a positive number, right? This right here is always going to be positive. It's never going to be negative because this is squared. Okay, it can be 0 if we plug the 1 and the 3 in, right? We plug the 1 and the 3 in, that would give us 4. And then anything else we plug in, we're going to get something greater than or equal to 4. Okay, so all the values that we plug in are going to be greater than or equal to 4. And the only point that's going to give us a 4 is the 0.13. You see that? So from that, we can say that f of 1,3 is a local minimum. Okay? And in this case, it's also an absolute minimum because there's nothing else that's going to be smaller than that. And if we look at the graph here, we can kind of sketch this graph. So we got the 0.134, right? Because if we plug the 1,3 in, we get 4 as an answer. So you're looking at a point of 134, and all the values are larger than that. And what do we get there? It's an elliptic paraboloid. And you can see that's a local minimum there. And it's also, in this case, it's an absolute minimum. Okay? All right, let's look at the next example. Find the extreme values of f of xy equals y squared minus x squared. All right, so we've got the partial with respect to x is equal to negative 2x, and the partial with respect to y is equal to 2y. All right, so if we take negative 2x equals 0, that means x equals 0, and we got 2y equals 0, that tells us y equals 0. And so our critical point is 0, 0. Okay. All right. So let's look at this and see if we can determine if we have any extreme values, maxes, local max, local mins. All right. So let's look at points on the x-axis. Okay, we look at points on the x-axis. That means y is equal to 0. So f of xy is equal to negative x squared, which is less than 0 if x, not less than or equal to, less than 0 if x does not equal 0. And then we look at the points on the y-axis. That's where x would be 0. So f of xy would equal y squared, which is less than 0 if y does not equal 0. Okay, so where did I get this and this? Well, if y is 0, I plug the 0 into here, I just get negative x squared. That's where that comes from. And then when x is 0, plug that in, I get the f of xy is equal to y squared. Okay? All right. Now, so what we're doing here is I'm not going to be able to draw this worth a flip, but let me see what I can do. If we look at that value, or if we look at it, so if I'm going along the if I'm looking at points on the x-axis, okay, you know, it's going back. The x-axis continues that way. The y-axis continues that way. So if I'm going along the x-axis, see, you got to understand that these values are negative. You see that? It's coming like this. It's, you know, something like this. It's negative. I can't draw it that good, but that's what it's doing. And then if I'm going along the y-axis, the values are positive, so they're going up like this. Okay, and I can't draw this thing good, but it's, you know, you're gonna have something like, let me see if I can make it look halfway decent. I know I can't, but it's kind of like looks like a saddle. So you can see around this point here, we've got the x values coming down this way. Okay, so that point would be like a maximum, but if we look in the y direction, we got points going this way, so this would look like, it'd be like a minimum. So it can't be a maximum and a minimum. And so this solution here, so we would say that 0, 0 is not an extreme value. And so that's how we can look at that. All right. And it would actually be called what? That would be what? A saddle point. Okay? And we'll get into that in a minute. But that's the concept of that. Okay, so we looked at an example where we determined that, hey, we've got a minimum value, and we looked at another one where we said, well, there's no extreme value there because it's depending on which axis you're going down, it's a max or a min. And, you know, that could be kind of, I guess some of them could be difficult to see. We wouldn't want to have to go through that every time. And so here we have it. We have the second derivative test. All right. And this is a way to determine if it's a local max, local min, or saddle point. All right. So the second derivative test says, suppose the second partial derivatives of f are continuous on a disk with center AB, and suppose that the partial with respect to x and the partial with respect to y both equal 0. Let D equal D of AB, D evaluated at that point. So that's is equal to the second partial with respect to x of AB times the second partial with respect to y of AB minus the second partial of f with respect to x and then y of AB squared. So this is D right here. This is you have to know this formula here. Okay, that's D. So if D is positive and the second partial with respect to x is positive, then we have a local minimum. And if D is positive and the second partial with respect to x is negative, then we have a local maximum. And if D is negative, then AB is a saddle point of f. Okay. And then we have a note here. If D is equal to 0, the test gives no information. F could have a local maximum or local minimum at AB, or AB could be a saddle point of F. That's if we get D equals 0. And then we have another note here to remember the formula for D. It's helpful to write it as a determinant. So if we write it as a determinant, remember when you find the determinant of this, it's just this times this minus this times this. And remember, this partial is the same as this partial. So when you multiply them, you can just write it as the partial with respect to x, y squared. Okay, so this is one way. This is one way that you can remember the formula if for some reason you forget it. But you know, the easiest thing to do, just remember it. All right. So here it says find the local maximum and minimum values and saddle points of this function right here. So we need to find the partial with respect to x and the partial with respect to y. So the partial with respect to x is equal to 4x cubed minus 4y. And the partial with respect to y is equal to 4y cubed minus 4x. Okay, so I get 4x cubed minus 4y equals 0. And so this is going to end up giving me y equals x cubed. Okay, so one thing that you've got to understand about these problems here is sometimes the most difficult part is just solving those first partials for setting them equal to 0 and solving them. That can be the most difficult part. Okay. All right. So now if we take 4y cubed minus 4x equals 0, well, that gives me y cubed minus 4x equals 0. I'm sorry. Y cubed minus x equals 0. So I just divided everything by 4. Now, to solve this, well, I know that y is equal to x cubed. So I can take the x cubed and plug it in for y. So that's going to give me, let's do it over here. That's going to give me x cubed cubed minus x equals 0. So that's x to the 9th. X to the 9th minus x equals 0. So that's x times x to the 8th minus 1 equals 0. So x times x to the 4th minus 1 times x to the 4th plus 1 equals 0. So that's x times x squared minus 1 times x squared plus 1 times x to the 4th plus 1 equals 0, which is x times x minus 1 times x plus 1 times x squared plus 1 times x to the 4th plus 1 equals 0. So we did all that factoring. And so when you set each of the factors equal to 0, we're going to get x equals 0, or x equal 1, or x equal -1. See, these two factors, they'll never be 0. So we just set these three here equal to 0, and that's what we get. And so now we need our y values. So here I can see I have y is equal to 0 cubed, which is 0. Y is equal to 1 cubed, which is 1. Y is equal to -1 cubed, which is -1. So I just took each of these values and plugged them into here to get my y value. So that is going to give me critical points at 0, 0, right? When I plug the 0 in, I got 0, 1, 1, and -1. Whoop. -1, -1. There's my critical points. Now, what do I need? I need the partial, the second partial with respect to x. So remember, the partial with respect to x is this, and then I take the partial of this with respect to x, which that's going to give me 12x squared. And then the partial x y, well, I mean, it doesn't matter which one, but if I take the partial of this with respect to y, that's going to give me what? -4. And see, if I take the partial of this with respect to x, that's going to give me -4. I mean, like I said, remember from when you learned how to do partial derivatives, it didn't matter which one, they're the same. And then I have the second partial of y with the second partial of f with respect to y, which that's going to be, this is the partial with respect to y, which that's 12y squared. Okay, so now let's test 0, 0. Okay, so what do I have to do to test 0, 0? Well, remember for d, where is it? It's right here. Remember, I need to evaluate each one of those second partials at the critical points. Okay, and which, you know, I mean, it's pretty easy to do here. So we've got the second partial evaluated at 0, 0 is equal to 0. The second partial with respect to y at 0, 0 is equal to 0. And the second partial xy evaluated at 0, 0, well, you can see that's just always -4. So for here, I'm just taking the zeros, plugging it into here. For this one, plugging it into here. And this one, well, that's just constant. So that's going to always be -4. Okay. And so now we can see that d is equal to 0 times 0 minus -4 squared, which is equal to -16, which we can see that is less than 0. D is negative, right? And what did it say up here? If D is negative, then there's a saddle point. See that? There's a saddle point. And so we would come down here and say 0, 0 is a saddle point. And so there you have that. All right, now let's test the next one, 1, 1. So I've got the second partial, 1, 1. Well, that's equal to 12. The second partial with respect to y of 1, 1, that's equal to 12 also. We're just plugging the ones in for x and y. And then this one is -4. So for this one, I get d is equal to 12 times 12 minus -4 squared, which when you do that calculation, you get 128, which is greater than 0. So d is positive. So what do we have to do up here? Well, d is positive, then we look at the second partial with respect to x and see if it's positive or negative. If it's positive, we have a local minimum. If it's negative, we have a local maximum. And we can see up here that the second partial is positive. So f of 1, 1, which equals -1, is a local minimum. Okay. And then we do the same thing with the point -1, -1. Well, that's equal to 12. Whoop. That's equal to 12. And that's equal to -4. And we get d is equal to 12 times 12 minus -4 squared, which is 128, which that's positive. And we have the second partial is also positive. And so f of negative 1, which is equal to negative 1, is a local minimum. And there's your answer. All right, so it's not bad. Let me circle all of that so you can see it's pretty easy. It's not bad at all. Not bad at all. Okay, piece of cake. All right, so let's look at this next example. It says find and classify the critical points of the function, this function right here. All right, so let's start off by finding the first partials, okay, and see what we get. So we've got partial with respect to x is equal to 20xy minus 10x minus 4x cubed. And then the partial with respect to y is, let's see, that's going to be 10x squared minus 8y minus 8y cubed. Okay. All right, so let's take this one, 20xy minus 10x minus 4x cubed, and let's set that equal to 0. So I can actually come up here and I can factor out a 2x, and that's going to leave me with 10y minus 5x minus 2x cubed equals 0. Okay. And that's not 5x, that's just 5. Okay, so that's what we get when we set it equal to 0. So we're going to get x equals 0 or 10y minus 5 minus 2x cubed. No. That's squared. Whoop. This one's cubed, and then when we factor out of x, that goes to a squared. Good thing we caught that. Okay. All right. So let's see what we get here. All right. So what do we get here? Well, we will have negative 8y minus 8y cubed equals 0. All right. See, if we take this and set it equal to 0, well, when x is 0, if I plug the 0 in for x, I'm just left with this part right here. Okay, see that? Just left with that. So we have negative 8y times 1 plus y squared equals 0. So I get y equals 0. So I have a critical point at 0, 0. Okay, so we have a critical point here, and I'm going to mark that with a little star because I'm going to have to use that later. Okay, this part right here, this 1 plus y squared, that'll never be 0. Okay, so that takes care of where x is equal to 0. Now let's look at this one. Okay, so if you look at this, that equals 0. So if you take 10y minus 5 minus 2x squared equals 0, you can see that we get 2x squared is equal to 10y minus 5, right? If I move the 2x squared over here. And so that's going to give me x squared is equal to 5y minus, and then 5 divided by 2 is 2.5. Okay, so that's x squared. So what I'm going to do is I'm going to take this part right here, and you see how that's x squared? I'm gonna put that in for x squared here. So, and I tell you what we're gonna do here. When we take this 10x squared minus 8y minus 8y cubed equals 0, I'm going to write this as 5x squared minus 4y minus 4y cubed equals 0. I'm going to divide everything by 2 just to get the number smaller. And so now I have 5 times, and then I'm going to put this in the place of that. I get 5y minus 2.5 minus 4y minus 4y cubed. Okay. And so now let's multiply this out. So that's 25y, and then 5 times 2.5, that is 12.5 minus 4y minus 4y cubed. Oh, and by the way, all this equals 0. And so that's going to give me negative 4y cubed minus 21y plus 12.5 equals 0. Now, obviously, when you go to solve this, you're going to need to using a graphing calculator. And I'm not going to pull up a calculator or anything. You could use graphing software. You could graph this thing. And then all you want to do is where that graph crosses the x-axis, go and find what those point coordinates are and figure out what the y coordinates are. Okay, figure out the y coordinates. All right, so when we use a graphing calculator, we get y is equal to negative 2.5452. We get y is equal to 0.6468, and y is equal to 1.8984. And I know if you're one of my students watching this, you know, we're so mean where I teach, we don't let them use calculators. They're going to say, well, what do we do on the test? Well, obviously, we're not going to give you one like this on the test. So you won't have to really worry about that. All right, so we got the y coordinates, and now we need the x coordinates. So from the equation, x squared equals 5y minus 2.5. Okay, we're taking this. We get x is equal to plus or minus the square root of 5y minus 2.5. And so what we would need to do there is we would need to take each one of these values, plug them in to get our x values. So when y is equal to negative 2.5452, okay, well, we can see x has no real values. And why is that? Well, we'd have a negative number under the radical sign, underneath the square root. And then when y is equal to 0.6468, that tells us that x is equal to plus or minus 0.8567. And then when y is equal to 1.8984, x is equal to plus or minus 2.6442. So like I said, you just take each one of the y values, plug them into here, and that's what gives you your x values. All right, so obviously we're not going to have a whole lot of room here, but we'll see if we can squeeze it in. So I got my critical points. Okay, I'm going to just make a little table here. So we got a critical point of 0, 0. We've got a critical point of plus or minus 2.644. Let's just round it to 2 decimal places. 2.6419, right? Because when I plugged in for this y in, I got this. And then our last critical point is 0.86. And, well, let me write plus or minus. We've got plus or minus 0.86. and the y value was 0.64, well, 0.65 when we round it to 2 decimal places. And in this case, if we take each one of these points, okay, you take each one of these points and we plug them back into the original equation. Now, when we do that, now look, it's not going to make any difference whether we plug the plus or the minus in, because remember, the x is plus or minus. That's not going to make any difference, because notice all the x terms are raised to an even number, so they're going to give us positive. So we're going to get the same answer whether we plug the positive or negative in. And so our f value is going to be 0 for this one, and for this one 8.5, and for this one negative 1.48. That just gives us the f value. That's f evaluated at those points. And then we need the f, the second partial of f with respect to x. So if I take the second partial of f with respect to x, I'm just going to kind of squeeze that in right here. That's going to be, 20y minus 10. And if I do the second partial y with the second partial of f with respect to y, that's going to give me negative 8 minus 24y squared. And then if I do the partial x y, that is going to give me 20. Okay. And so if we take each one of those y values, okay, and plug them into this one, because what do we have to know? We have to know what if this is positive or negative, and then we have to know if d is positive or negative. So if we plug each of those into the second partial with respect to second partial of f with respect to x, we're going to get negative 10, negative 55.93, and negative 5.87. And then for d, so we're plugging it into that formula. Okay, we did this in the last example, so that's why I'm not going to go through all this. You gotta plug all those in. You know, you got to do all of this to that formula d, each one of those numbers. This is going to give you 80. This is going to give you 2488.72, and this one's going to give you negative 187.64. And so you can see here, f double prime is negative, d is positive. So that tells us we have a local maximum. And then same thing here. The second partial with respect to x is negative, d is positive. So that's a local maximum there. And then here d is negative, and so we can see that as a saddle point. And there's your solution. So you have a local maximum at f of 0, 0, which equals 0, and a local maximum at f of this point, which is equal to 8.5. And then here you have a saddle point. Okay? All right, so I hope all of this is making sense. All right, so let's continue on to the next example. Okay. It says find the shortest distance from the point 1, 0, negative 2 to the plane x plus 2y plus z equals 4. All right, so we're going to take the distance from any point x, y, z to the point 1, 0, negative 2. Any distance there. So do we remember the distance formula? Well, the distance is what? X minus 1 squared plus y minus 0 squared, which is just, well, we'll write it out. Y minus 0 squared, and then we have z minus negative 2, which is z plus 2 squared, and it's the square root of all that. Okay. All right. So we have the point. Let me write it. I'm going to write it right here. We have x, y, z lies on the plane x plus 2y plus 2 equals 4. Okay? Because we want to know the shortest distance from this point to this plane. So our point xyz, that's the point on the plane. Okay, so from this point, where do we have to go onto the plane to a point xyz in order to get the shortest distance? All right, so we have z is equal to what? 4 minus x minus 2y, right? If we solve this for z. So that's going to give us d is equal to the square root of x minus 1 squared plus y squared plus, and then I'm going to take this and plug it in for z. I'm going to plug in 4 minus x minus 2y plus z. I'm sorry, not plus z, plus 2, and that's all squared. So that's just going to give me what? 6 minus x minus 2y squared when I combine like terms. So basically what I'm doing, I'm getting everything in terms of x and y. Okay? And so when we minimize this, we can minimize it by minimizing d squared. Okay? It's easier to take the derivative. Let me write this. This is actually, once we square both sides, that's what we're going to use as our function. Okay, so we're going to minimize that. So now we need the partial with respect to x and the partial with respect to y. All right, so we've got the partial with respect to x. So this is chain rules. That's going to be 2 times x minus 1, subtract 1 from the exponent, times the derivative of what's inside the parentheses, which is just 1. The derivative of this is 0. And then the derivative of this, that would be 2 times 6 minus x minus 2y to the first times negative 1. And so that's going to give me, well, let's see, how do we want to do this? We'll do 2x minus 2 minus 12 plus 2x plus 4y. I'm just distributing the negative 2. Okay, and so I get the partial with respect to x. We will combine like terms. I'm going to get 4x plus 4y minus 14. And then I need the partial with respect to y. That part right there is 0, so that's going to be 2y plus 2 times 6 minus x minus 2y times negative 2, which that is going to be 2y, and let's see if I can do this in my head. Is that going to be minus 24 plus 4x plus 8y. I hope I got that right. I did it in my head, so I could miss something. So that's going to be 4x plus 10y minus 24. All right, so I think I did that. I think I got that. So there's our first partials with respect to x. So now we have 4x plus 4y minus 14 equals 0, and 4x plus 10y minus 24 equals 0. So this is, if you look at this, this is just a system of equations. 4x plus 4y equals 14. And 4x plus 10y equals 24. So you've just got a system of equations to solve. You can use addition method, and so you're going to get your critical point is going to be 11/6, 5/3. That's what you should get when you solve for x and y. You should know how to solve that. If you can't solve that, then you're not going to be very successful in this calculus class. Okay? All right. So now we need the second partial with respect to x. So that's the partial of this with respect to x. That's going to give us 4. And then we need the second partial with respect to y. That's going to be what? 10. And then we need the partial with respect to x, y. And so that's going to be 4. All right. And so now we have d is equal to 4 times 10 minus 4 squared, which is equal to 24, which that is positive. And then we also see that the second partial with respect to x is also positive. So we can say f has a local minimum at 11/6, 5/3. And so now the distance d is equal to, well, what's d? D is, where is it? That's this thing right here. And what I'm going to do is I am going to lasso this thing, and I'm going to bring it down here. Oh, was it not? Now, why didn't it get all of that? Let's hit the undo. Okay, I don't know why it's not picking it all up. I'll just rewrite it. So d is equal to the square root of x minus 1 squared plus y squared plus 6 minus x minus 2y, all of that squared. So what I'm going to do now is I'm going to take the x and the y and plug it into here. Okay, you're plugging all that in. So when you do that, you would get 5/6 squared. Like if I plug 11/6 into there, that would be 11/6 minus 6/6, which is 5/6 squared, plus 5/3 squared, plus, and then when you plug the x and y into there, you end up with 5/6 squared. And so d is equal to 5 square root of 6/6, and this is your shortest distance. All right. So, I mean, it's not bad. So you can see that finding local max and mins is not difficult to do. I mean, all you're doing is you're finding your partial derivatives, your first partial, second partials, and then you're plugging it into your formula d, and you just got to see is d positive or negative, is is the second partial of f with respect to x, is that positive or negative? And then that tells you if you have a local max or min. Okay? All right, so let's look at this next example. It says a rectangular box without a lid is to be made from 12 square meters of cardboard. Find the maximum volume of such a box. All right, so let's see what we've got here. We've got a rectangular box. Now, you work problems similar to this in the first calculus, but do you remember the difference? Or one of the, is there one thing that you noticed? Well, remember in single variable, what would the problem tell you? Or most of the time when you worked a box problem, it told you what a box with a square base. So you knew the bottom was the same. That was X and X. But now it's just telling us a rectangular box. So that's X, Y, Z. We've got the three variables here. And what do we want to maximize? Well, we want to find the maximum volume. So that means we've got V is equal to X times Y times Z. Okay. And then just like in single variable, when you had an area or something like that, and like, you know, the area of a rectangle was what? X times Y. Well, what would you do? You would get it all in terms of X or all in terms of Y. Well, that's what we're going to do here. We're going to get everything in terms of X and Y. All right. So what other piece of information does it give us? Well, it tells us that a lid is to be made from 12 square meters. So all of this is 12 square meters. Okay. So if you look at this, and notice it doesn't have a lid. All right, that's a big deal because then we don't have to include the top. So we know that if we take the area 2x times z, right? See, the area of this face right here, that's x times z, and then we have another one over here. So we've got x times z plus x times z, so that's two of them. And then we've got plus, and then we've got this front face here. You see that? We got the front face, and we would also have the back face back here, right? What are those areas? Well, that's y times z, and we have two of them. So that's 2yz plus, and then we have what? We have the bottom here, right? We've got the bottom. That's x times y, and that area there equals 12. And so you can see that we have 2xz plus 2yz equals 12 minus xy. And so if we factor out a z, we're left with 2x plus 2y, so that's 12 minus xy over 2x plus 2y. That's z. And let's write it z equals 12 minus xy over 2 times x plus y. Is that going to help us factoring out that 2? I don't know. It might. We'll see. All right. So now we have our volume. So our volume is equal to x times y, and in the place of z, I'm going to put this. So that's 12 minus xy over 2 times x plus y. All right, which that's going to give me v is equal to, what is that? 12 xy minus x squared y squared over 2 times x plus y. All right. So there's our volume. All right. So now what we have to do is we have to take the partial with respect to x. Now, I'm going to work out finding the partial with respect to x. And then I'm probably going to have to erase it because I'm not going to have enough room to work everything. But I will work that part out. The partial with respect to y, I'm not going to show the work for that. It's going to be similar to the partial with respect to x. Okay, I'm just going to do one of them. Okay. All right. So we've got the partial with respect to x. So this is a quotient rule, right? So remember, it's with respect to x, so y is treated as a constant. So it's the derivative of the numerator, which is going to be 12y minus 2xy squared. That's the derivative of the numerator times the denominator. Minus the derivative of the denominator. Okay, what's the derivative of the denominator? Well, that's just 2, right? See, if I wrote this as 2x plus 2y and I took the derivative of that with respect to x, that would just be 2. And then that's times the numerator, 12xy minus x squared y squared. And then this is all over the denominator squared. All right. So let's see what we get here. All right, so we're going to take this and we're going to distribute it. So that's 24, okay? 24y times x plus y minus 4x y squared times x plus y minus 24xy plus 2x squared y squared. And this is all over 4 times x plus y squared. All right. All right, now let's clear these parentheses here. So that's going to give me 24xy plus 24y squared minus 4x squared y cubed minus 24 minus 24xy plus 2x squared y squared. And let me check and make sure I have no stupid mistakes anywhere, because I don't want to do this and then there's a mistake. Okay, so I do have a mistake right here. So we distribute this to the x. That should give us 4x squared y squared minus 4x squared y cubed. Multiply to that and then that. And then minus 24xy plus 2x squared y squared. And that should be it. And so now that is going to give us, let's see, this and this cancel out. And so we are left with, let's see, 24y squared. Okay, 24y squared minus 4x squared y cubed. No, so I do this, let's see, this times this is 4x squared y squared. This times the y would be minus 4x y cubed. So we've got the minus 4x, come on, erase. We got the minus 4x y cubed. It just gets all jumbled up. Minus 4x y cubed. And we did this one already. And then for this one, we got minus 4x squared y squared plus 2x squared y squared. That's going to give us minus, let's change colors. That's going to give us minus 2x squared y squared over 4 times x plus y squared, which that is going to give us, let's factor out a y squared times 12 minus 2xy minus y squared over 2 times x plus y squared. So 2 goes into 4, 24, 4, and 2. That's where that comes from. And then I factored out a y squared. And when I factor out a y squared, that should have left me with x squared, not y squared. So there's your partial with respect to x. And when you go and do the partial with respect to y, you're going to do the same thing. Okay, it's going to be similar. Just take your time. It's easy to get lost in all this. You saw I messed up a couple of times, but just go back and double check yourself, or do the partial with respect to x, get your answer, and then go and do it again and see if you get the same thing. So, but yeah, that's how you do it. So I'm going to erase all this, and I'm just going to write these first partials down. So because I won't have enough room if I do that. But there it is. Okay. All right. So here's your partial of v with respect to x and with respect to y. So what do we need to do? We need to take the partial with respect to x, set that equal to 0, which that means that what? Y squared times, where is it? 12 minus 2xy minus x squared equals 0, right? Because when is it 0? When the numerator is 0. And then we take the partial of v with respect to y equals 0. And so that means x squared times 12 minus 2xy minus y squared equals 0. All right. So to solve each of these, obviously you can see here, if we take the y squared equals 0 and the x squared equals 0, we would have y equals 0 and x equals 0. Okay, and if x and y were 0, that would give us a volume of 0. So we know that's not it. That's not the answer. So we're not going to get a volume of 0. Okay. So what do we need to do? So we need to solve 12 minus 2xy minus x squared equals 0. And we need to solve 12 minus 2xy minus y squared equals 0. And can you see, if you set these two equal to each other, you see that if you set them equal to each other, what happens? You see how the 12 and the 2xy's, they would cancel out, and we would be left with x squared equals y squared. And so that tells us that x is equal to y, and we know x and y must be non-negative, right? Because we're dealing with the length of the side of the box. And so now what we can do is we can take x equal y, we can take that, we can plug it into either equation. Okay, it doesn't matter which one. So I guess what we'll do, we'll take the x and just plug it into here. Okay, plug it in there for y. And so that would be 12 minus 2x times x minus x squared equals 0. And that is going to give us, let's see, what is that going to give us? That's going to give us 12 minus 2x squared minus x squared equals 0. Well, that works out nice, doesn't it? 12 minus 3 minus 3x squared equals 0. So move that over. 12 equals 3x squared. So x is equal to 2. And if x is equal to 2, y equals 2. Because we just take the 2, you can plug it back into here because we know y equals 2. And this is an absolute maximum. This is our critical point, 2, 2. And that would be our absolute maximum is going to occur at our critical point of v. So it occurs when x equal 2, y equal 2, right? And z is equal to what? Well, we take the 2's and plug them into this. So that's going to give us 12 minus 2 times 2 over 2 times 2 plus 2, which that's going to give us a 1. And so the maximum volume is what? X times Y times Z, which is 4 cubic meters. And there you have it. All right. So, you know, like I said, the most difficult part is going to, probably the most difficult part of these problems is going to be where you take the partial derivatives and set them equal to 0 and solve. That's probably what you'll have the most problems with. All right, so let's look at this one. So it says let AB be a point in the domain D of a function f of 2 variables. Then f of AB is the absolute maximum value of f on D if f of AB is greater than or equal to f of xy for all xy in D, and an absolute minimum value of f on D if f of AB is less than or equal to f of xy for all xy in D. Extreme value theorem for functions of 2 variables. If f is continuous on a closed bounded set D in R2, it's going to be in the xy plane, then f attains an absolute maximum value f of xy and an absolute minimum value, absolute maximum value of f of x1, y1, and an absolute minimum value of f of x2, y2 at some point xy and x2, y2 in D. So to find the absolute maximum and minimum values of a continuous function on a closed bounded set D, find the values of f at the critical points of f and D. So we're going to find our critical points, and those points are going to be in D. Find the extreme values of f on the boundary of D, and the largest of the values from steps 1 and 2 is the absolute maximum value, and the smallest of these values is the absolute minimum value. All right, so let's look at an example. All right, so it says find the absolute maximum and minimum values of the function, this function here, on the rectangle 0 to 3, x is between 0 and 3, y is between 0 and 2. So the best thing to do here is just let's plot the rectangle. Okay, let's plot this rectangle. And so we've got from on x we're going from 0 to 3, on y we're going from 0 to 2, and here we have our rectangle. This would be the point 3, 0, this would be the point 3, 2, this would be the point 0, 0, and this would be the point 0, 2, right? Now, we've got to look at each one of these lines, okay? We've got to see the value on this boundary here, on D. So let's label this line L1. Let's label this one L2, L3, and L4. Okay. So let's take a look at our function. So on line 1, you noticed on line 1 that y is 0 the entire time. Okay. Y is 0 the entire time. So if I take it when y equals 0 and I plug it into here, that is going to give me f of x0 is equal to x squared, right? If I plug 0 in for y. And this is from 0 less than or equal to x less than or equal to 3. Okay. And actually what I should have done first is found the critical point. I'll do that last. Okay. I could have done the critical point first. I didn't. But anyway, there we go. We're gonna do this. We gotta find our critical point also. All right. So you see this function here, x squared. that's an increasing function, right? Its minimum value is 0, and then it's increasing from there because it's like a parabola opening upward. All right, so we know it's an increasing function, and if I do f of 0, 0, that is equal to 0 squared, which is 0. And if I do f of 3, 0, that's equal to 3 squared, which is equal to 9. Okay, all right. Now, why did I plug in 0, 0 and 3, 0? Why did I do that? Well, since it's an increasing function, well, this is going to give me my smallest value. This is going to give me my largest. Doesn't matter what I plug in between, because from here, it's just steadily, see, from this point here, 0, 0, it's steadily increasing. Okay. All right, now let's look at L2. Okay, so when we look at L2, this line here, you notice that x is 3. X is equal to 3. And so that's going to give me f of 3y, right? I'm replacing the x with the 3. That's going to give me 9 minus 4y. All I'm doing is plugging the 3 in here. Okay, 3 squared is 9. Plug the 3 into there. That's 3 times 2 is 6. Negative 6y plus 2 is negative 4. Okay, and this is from when y is between 0 and 2. And you see that this is a line, has a negative slope, so it's decreasing. Okay, so I'm going to test the 2 points here. Okay, I'm going to do f of 3, 0, which when I'm plugging 0 in for y, that's going to give me 9. And then f of 3, 2, I plug the 3 in for x, the 2 in for y. So basically I'm just plugging 2 in for y. That's going to be 9 minus 8, which is 1. Okay. And you can see here, this is a minimum, and this is a maximum, right? This is a maximum, and this is a minimum. But we are looking for the absolute max and min, okay? And now let's look at L3. So L3, we notice here that y is 2 the entire time. You see that? We've got y is equal to 2. So that's going to give us f of x2. So we're plugging 2 in for y. And so that's going to give us x squared minus 4x plus 4. And that is on the interval 0 to 3. X is between 0 and 3. Well, this might be kind of difficult to see, but if we look at this, f of x2, and let's say we factor this thing, okay, can you see that the smallest value is going to be when we plug the 2 in? Whoop. It's going to be when we plug the 2 in. That's going to be the smallest value when we plug 2 in. That's going to give us a 0. Okay. So if you look at this, if you look at f of 0, 2, okay, we're going to look at this point right here. So if we plug 0, 2 into this, that's going to give us, what is an answer? 4. And then let's plug in f of 2, 2. We know that's going to give us a 0. Could we get anything smaller than 0? No, because this is squared. So at the point 2, 2, when x is 2, that's when I'm going to get my smallest value. That's actually going to be 0. And we'll see that's a minimum. And then we will try this endpoint, f of 3, 2. F of 3, 2. So we plug the 3 in here. That's going to give us 1. So right here at 2, 2, that was a minimum. And we can see this is a maximum. Okay. And now we need to look at L4. So at L4, you can see what? X is 0. You see the X coordinates are 0 on L4. So when X equals 0, we get f of 0y is equal to 2y. And that's when y is between 0 and 2. Okay, right, because I take the 0 and I plug it into here. So that would be 0, 0. I'm left with just 2y. And we can see that this is an increasing function, right? It's a line with a positive slope. It's going to be a line with a positive slope, but it's increasing. So if we do f of 0, 0, I'm going to evaluate it at 0, 0, and I'm going to evaluate it at 0, 2. So f of 0, 0, that's 0, and then f of 0, 2 is 4. So I can see this is a minimum, and this one is a maximum. All right, so that's where I went and I tested the boundaries. All right, so now what I have to do is I have to go and find my critical number. I probably should have done that first, but I didn't. I was concentrating on explaining this part of it good to you that I just completely forgot about the critical point. So let's write the function down again. Let's write f of xy. I'm just writing our function down. Equals x squared minus 2xy plus 2y. So to find our critical point, I'm going to do the partial with respect to x. So that's going to be 2x minus 2y. And the partial with respect to y, that is going to be negative 2x plus 2. All right. So here you can see we get x equals 1 when we set this equal to 0. Let me set it equal to 0. Negative 2x plus 2 equals 0. X equals 1. And then I plug that into here. 2x minus 2y equals 0. So if I plug the 1 in for x, that's 2 minus 2y equals 0. So I get y equals 1. So my critical point is 1, 1. Okay. And what do I get? F of 1, 1. Well, if I take, here's our function here. If I plug 1 into here, that's going to give me a value of 1. Okay. So now, what do? Well, we go through and we look, and you can see that we have a maximum of 9. This is the largest value. And then let's see. Well, I mean, and we have it here too, but that's the same point, 3, 0. And then we have, it looks like the smallest value is 0. Do we have a 0? Yep, we have a 0 right here also. And then we have the 0 here. But at the point 0, 0, we already had that up here, which gave us 0. So from all of that, you can see that we have an absolute maximum on D is f of, now what was our largest value? The 9, right? And that occurred at 3, 0. Is f of 3, 0, which equals 9. And then we have an absolute absolute minimum on D is where? Well, that's where we're at 0. So that occurred where? At 0, 0, and it occurred at 2, 2. So D is f of 0, 0, which is equal to f of 2, 2, which equals 0. There's your absolute minimum, and there's your solution. And that is all of this section. So I hope you enjoyed that. I hope it helped. Check out my other videos. Give me a like, share, subscribe, comment, and I will see y'all in the next one. Later.